All right, so carpenters use a level to find out if a surface is perfectly horizontal. When a carpenter places the level on its surface that is perfectly horizontal, the air bubble stays in the middle. So it kind of looks like this. See this here? Stays in the middle of the horizontal tube. The metal, alcohol, and air in the level present three phases of matter. Okay, so the metal, this part right here, is a solid. There's liquid in here, water, and then there's a gas. So how can shape and volume be used to classify materials? And materials can be classified as solids, liquids, or gases based on whether their shapes and volumes are definite or they vary. So solids do, what do these four objects have in common? A pencil, a quarter, a book, a cafeteria tray. They all have a recognizable shape and they all take up a certain amount of space. The materials in these objects are called the solid state, or they're in the solid state. Now, solid is a state of matter in which the materials have a definite shape and a definite volume. Solids, like this copper here, have definite volume. The copper atoms are packed close together and are in an orderly arrangement, okay? Almost all solids have some type of orderly arrangement of particles at the atomic level. Liquids are a little different because, well, let's start with this question. How good are you at estimating whether the juice remaining in an almost empty bottle will fill in a glass or will fit in a glass? The shape of the liquid changes as you move it from the bottle to the glass. In other words, the liquid has the same shape as its container, and it can be poured from one container to another. Liquid is a state of matter in which a material has a definite volume, but not a definite shape. Liquids take on the shape of the container they're in. So liquids at room temperature, like mercury, can form and mercury is a metal, but drops of mercury on a flat, clean surface have a round shape. Mercury in a container has the same shape as its container. The mercury atoms are close together, but their arrangement is a little more random than the arrangements of atoms in solid copper. Okay. So if you look at it at a microscopic level, it's not as ordered. So now the last state of matter, gas. Let's think of it like this. If you were asked to name a gas, what would you say? Air, which is a mixture of gases, is probably the most obvious example. Okay, gas is a state of matter in which a material has neither a definite shape nor a definite volume. A gas takes the shape and volume of its container. These balloons are filled with helium, which is a colorless gas that that's less dense than air. So 2 of the balloons are teardrop in shape and 2 are disc shaped. The shape of the helium in the balloon is the same as the shape of the balloon itself. The volume of the helium in a balloon is equal to the volume of the balloon. So they take on the shape of their container as well. If you look at their molecules, though, they're spaced out a little bit further apart. Okay? The helium atoms in a balloon are not arranged in a regular pattern. They are in random locations throughout the balloon. Because of the space among the helium atoms, a large amount of the helium can be compressed into a metal cylinder. When the helium flows from the cylinder into the balloon, the helium atoms spread out. The helium can fill balloons with much more volume than in the cylinder. So when you go to get your balloon, they have like a big tank, and they hook it up to the balloon, and there's the stuff in the tank is pressurized, so they're cramming all those atoms into the tank, and the atoms are moving around quite a bit because they have a lot of kinetic energy. And when you let them out of the tank, once they get into the balloon, they kind of stretch out and go, you know. So there's other states of matter. About 99% of all matter in the universe exists in a state that is not as common on Earth as solids, liquids, and gases. At extremely high temperatures, such as those found in stars, matter exists as plasma. At temperatures near minus 273 degrees, groups of atoms behave as though they are a single particle. This is a fifth state known as the Bose-Einstein condensate. So there's two extremes, like really, really cold, it doesn't move hardly at all, the atoms or molecules. And then at a really, really high temperature, it's completely different, okay? So why was mercury used in thermometers? Well, until recently, mercury thermometers were used in homes and schools because mercury is a toxic substance and it can harm humans and other organisms. Schools no longer use mercury in thermometers, and people are encouraged to replace them for like their regular thermometers. But mercury had a interesting melting point, and it expanded rather quickly, so it was very sensitive to temperatures around room temperature. Why did people continue to use mercury thermometers long after they discovered it was dangerous? Well, if you look at, I'm going to show you a table in a second here. The densities over a temperature from 0 degrees Celsius to 150 degrees Celsius, the temperatures are given at 30-degree intervals. So if you look at mercury, the density changes, it decreases as the temperature increases, and also, here's the more important reason, the volume changes. So the warmer it gets, it will tend to expand, and so that allows you to have something that when the temperature goes up, because the mercury will expand in a thermometer, it'll go up, and you can put a gauge there. So the density decreases and the volume increases. So here's another question. How does a change in density affect the volume of a mercury sample? As the density decreases, the volume increases. Okay. If a thermometer contained a gram of mercury, how much would the volume of the mercury change when the temperature rose from 0 degrees Celsius to 30 degrees Celsius? And then for each increment. And so if we go back to the table, it looks like it changes about 0.0004 milliliters. So let's see what they say. Yeah. So it's a constant change of 0.00040. Okay. Why was mercury a better choice than liquid for a liquid in a thermometer? Notice that it starts at 0 degrees. Well, the change in volume of mercury is almost identical at each interval, so the spacing and the degree marks are consistent, and one of the obvious reasons is it's still a liquid at 0 degrees Celsius. Why was mercury in a thermometer stored in a narrow tube? With a much smaller change in volume per degree, the mercury must be in a narrow tube for the difference in height to be observed and measured. Okay, so it expands, but it expands very little. So it's kind of like a graduated cylinder, right? If we take a beaker and that's a 250 milliliter beaker like we did the other day and pour it into a graduated cylinder that only holds 100 milliliters, the graduated cylinder, because it's narrower, allows us to really be a little bit more precise in how much water we actually have. In other words, we can measure it by the milliliter a lot more accurately than in a beaker. So what this boils down to is kinetic theory. Now, kinetic theory of matter says that all particles of matter are in a constant motion, unless it's minus 273 degrees Celsius, but that really doesn't exist. So a ball thrown at 137 kilometers per hour has more kinetic energy than a ball thrown at 125 kilometers per hour. According to kinetic theory of matter, particles inside the solid baseball are also moving. The kinetic theory was developed to explain the behavior of gases. It can also help to explain the behavior of liquids and solids. So as you have more kinetic energy, that means that you're moving faster. So it's kind of a measurement of movement to some degree, what kinetic energy is. So how can kinetic theory and the forces of attraction be used to explain the behavior of gases, liquids, and solids? Well, the motion of billiard balls can be compared to the motion of particles in a gas. A cue ball strikes the ball, and the ball moves in a straight line until it strikes the other side of the table or another ball. When the moving ball strikes a ball at rest, the first ball slows down and the second ball begins to move. Kinetic energy can be transferred during these collisions. So, in a gas, when it's moving around, molecules or atoms are hitting each other and bouncing around. So in this photograph, if you take a look at it, you'll see that the cue ball, the white ball, will move in a straight line until it collides with the blue ball. Unlike billiard balls, the particles of a gas are never at rest, so they never stop. They slow down a little bit, but not really. They just keep moving. And I'm not going to read this whole slide, but basically the short version of it is if there's heat is a form of energy. So atoms can absorb heat energy, and the sun brings heat to Earth. So some atoms, based on their structure, absorb that heat energy and automatically convert it to kinetic energy. That's why some atoms will be at a gas phase at a lower temperature than others. It just depends on the atoms themselves and how they're structured. Some atoms that are smaller move around more, like hydrogen. Hydrogen has one proton, one neutron, one electron, right? So that one will move around. Actually, yeah. I got to think about that. It's much smaller than, say, lead. Lead has way more protons, way more electrons. So that doesn't move around as much, okay? So atoms will move in a straight line, then they'll collide into another one, and then they collide into the side of the container. This is also known as pressure. The more the atoms collide into stuff, the more pressure that gets built up inside the container. The total kinetic energy of the atoms pretty much remains the same. It just transfers from one atom to the other. There is a little bit of energy loss. So what about the forces of attraction? Well, between the collisions, one particle of gas, while it's moving apart and moving fast, the attractions are too weak to stop it from moving. But depending on the material itself, sometimes they are attracted, and that's so gases, the attraction is weak, or let me back up. The kinetic energy is much higher than the attraction. In a liquid, the kinetic energy is higher, but the attraction is high enough to kind of keep it together. And in a solid, the attraction is so strong, and there's very minimal kinetic energy, not a lot of movement of the atoms, basically. So the constant motion of particles in a gas allows the gas to fill the container of any shape. So these molecules are bouncing around, bing, 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 bing. So particles in a gas are in constant random motion. The motion of one particle is unaffected by the motion of the other particles unless the particles collide. Forces of attraction among the particles in the gas can be ignored under ordinary circumstances. And this is all sensitive to temperature. Some molecules that are lighter will be at a gas at a much lower temperature. And so if that's the case, they absorb heat energy, it converts to kinetic energy, and they move around. And the attraction among the atoms or molecules is it's just not more than the kinetic energy. So it's a gas at a lower temperature. How can kinetic theory and the forces of attraction be used to explain the behavior of gases, liquids, and solids? Well, the average speed of a Mercury atom is much lower than the average speed of a helium atom. And a lot of that has to do with mass. They're different masses. The particles in a liquid are more closely packed together than those of a gas. and then a solid is even more than a liquid. So the attractions of the particles in a liquid do affect the movement of the particles. So they'll move away, but then they kind of are attracted back. So they're kind of doing this thing, where with a gas, the movement is so great it just kind of leaves. So then mercury atom in liquid mercury can be compared to a student in a crowded hallway. The student's path may be blocked by other students moving in the other directions. The student's ability to move is affected by the interactions with the other students. So the atoms are closer together. Liquid takes the shape of its container because the particles of the liquid can flow to a new location. The volume of the liquid, for the most part, stays constant if the temperature is constant. In a liquid, there is a tug of war between the constant motion of particles and the attraction among the particles. So it's like, I'm going away, no, you're not. I'm going away, no, you're not. And so, like, if you think of water at a liquid temperature, this is what's going on. Like, this is a molecule of water, this is a molecule of water. So I'm constantly doing this, but when I add heat, the molecules absorb that heat energy, and if I get enough heat energy, that gets converted to kinetic energy, and then they separate and become steam. So how can kinetic theory and the forces of attraction be used to explain the behavior of gases, liquids, and solids? Solids have a definite shape and volume, and they do vibrate around, but it's much tighter packed, and basically the attraction is very strong. So in a copper tube, the copper atoms restrict their motion and keep each atom in a fixed location. So they're like this, right? Each atom vibrates in its own location, but it does not exchange places with its neighboring atom. So they're almost kind of like locked in together. It's a different analogy. It's like there's a string connecting the two of them, and so they can't just move around freely. So this would be like a movie theater, right? Everybody's sitting in the seat, they don't get up from the seat, and they're stuck in the seat, right? Now you can move within the seat. So if you look at the picture on the left, everybody's sitting still, and the one on the right, everybody's raising their hands. That's what happens in copper, is that they sit still, and maybe the electrons enter a higher energy state, but it doesn't move the whole atom. They're pretty much fixed.